Okay, so uh, today we're going to go through pages 5 through 8. These are differentiation topics, and feel like you're going to I feel like it's going to be something that you are feel pretty good about because we've kind of been using a lot of these topics even recently, right? So things like power rule, product, quotient, chain, implicit differentiation. We'll work through as much as we can today, and whenever we don't finish, I'll try to put homework on Wednesday. Wednesday, I'll check pages 19 through 23, basically the morning review from the upcoming quiz, and then pages 5 through 8, I'll check that Wednesday. For your quiz tomorrow, you really just want to focus on pages 19, or sorry, pages 21 through 23. On my morning review or on Friday, I recorded A through E, and then tomorrow I'm going to start with F through K, and I'll go back and I'll revisit A through E. So I think it's the best thing to review, but I think it's also good to look over packets 1, 7 through 18. These are all kind of circling around the same topics. So just look through those pages as well. The anti-derivative word problems from day 1 to day 2, that's not on the quiz. So starting Tuesday, we kind of focus in on just these topics that we can see on the small quiz. Make sure you bring your calculator, and I'll have a formula sheet on page 24 attached to your quiz. Okay. Any questions about quiz for tomorrow? Okay. So let's go to page 5. All right, so methods and skills to review: derivative rules, product rule, quotient rule, chain rule, implicit, and derivative inverse set of points. This is where we create the table, and we have to go through those procedures, but we'll go back and we'll definitely revisit number 6 because that's a very specific procedure that we follow for derivative of inverse set of point. These are, I think, the most commonly used rules on the AP exam. I say the big 3 are power rule, e to the u, and natural log. These are guaranteed. And there's no AP exam without these 3 rules showing up. And then the other common ones are tangents of u, sine and cosine, tangents, and secants. Those are the most common ones. Sine and cosine being the ones that you're almost guaranteed to see on AP exam as well. Product rule, quotient rule, and chain rule. We did a lot of practice with these rules recently. Chain rules as well. Power rule, that's probably the rule that we're most familiar with. But even so, there are quite a few conditions that we have to make sure it passes before we do power rule. There's a lot of ways to do power rule incorrectly. So first thing we do is make sure that your term is written as a rational exponent, square root of x to the 5th. I think that especially gives students some trouble because square root of x to the 5th is actually x to the 5/2. But a lot of students will divide it this way. They would say x to the 1/5, or they would say x to the 2/5. So yeah, those are incorrect, right? So the hidden number here is the 2, the square root, and then we do the 5 first, and then the 2. So if you forget these rules, then you kind of work backwards, right? You know that square root of x is x to the 1/2, and just ask yourself, well, where's that 1 and 2 coming from? 1 is coming from here, and 2 is coming from here, and you can see, oh, okay, the 1 on the right goes above, and then the root goes below. So if you know what square root of x equals, then use that to help confirm ones that are easily mistaken. Okay. So if there's a radical, we convert the rational exponent. Make sure you bring the variable to the numerator before applying power rule. We can't do power rule if variables in the denominator. And then third, we got distribute terms and resolve parentheses and fractional terms before power rule. So if there's any x stuck with another x with parentheses, we can't do power rule unless we can find a way to merge them all together. Okay. So let's try number one. Here are a bunch of terms that are all nicely separated. First term is ready, second term is ready, third term is ready, but the fourth and fifth term we have to rewrite before we can apply the appropriate rules. Okay, so not all these are power rule. You see the e to the 2x and natural log. These are e to the u and natural log rules. But go ahead and rewrite all the terms first, and then you can do power rule. You can do the derivative rule all at once. Okay, so this is what our function looks like after the rewrite. I just wanted to wait until every term is ready for derivative, and then I can do the derivative all at once. So I'm rewriting all the terms that are ready to go. The first three terms are ready to go. The fourth term, 3 over x squared, we can't do power rule in that form. That x has to come up first. Then we can do power rule. Again, root x to the fifth is x to the 5/2. Now we can jump into our derivative rule. Power rule for the first. Second term is e to the u times u prime. Natural log of u is u prime over u. Power rule, and then that 3 is a constant, so that 3 is going to go to a 0. Okay, try that so you can find the appropriate derivative rules. Okay, e to the 2x becomes e to the 2x times 2. Natural log of 4 minus x becomes -1 over 4 minus x. All right, take a look at number 2. Y equals cube root of 5 minus 3x squared. What's the big rule that we have to make sure we include for number 2? Chain rule, yeah. So rewrite it using parentheses. And then you can clearly see an outside and inside portion, identify them, and then do chain rule, outside derivative times inside derivative.
Okay, so we apply power rule for that parentheses of the 1/3. And then the separate space will multiply by the inside function derivative, and they'll just be connected together by multiplication. Do some cleanup here. Put it all under one fraction. A lot of different variations. Any of the variations are fine, but just be aware how to get to these variations, because on AP exam, if it's a multiple choice question, you have to find the form that matches the correct choice, right? Correct answer choice. Okay, number 3, given the function, find the equation of the tangent line. So hopefully we're comfortable with this process. You got to find the derivative. After you find the derivative, plug in the order pair to get that slope. Use the original equation to find the order pair, and then put slope form. F prime g minus f g prime all over g squared. Therefore, with your parentheses, the negative has to distribute through the f and the g prime. So what I like to do is I like to pull the negative 2x out in front. That way I can just distribute it along with the negative and not have to do it multiple times. And again, careful with quotient rules. We cannot cancel the 2 minus x squared as it stands. It feels easier, but it's attached to the minus sign. So we really have to combine your like terms before you do anything with the denominator. So in this case, I didn't really cancel anything out. I just got it to as clean as I could, and then replace all the x's with 1 to get to my slope. Order pair comes from the original equation, and then my slope form. Any questions with 3? And 4, y equals x squared sine 2x. Find the derivative. Dy dx means notation for derivative. The x squared is sine 2x. Hopefully we recognize that as 2 separate terms. The sine 2x is one term, but the 2x is inside that sine. So there's a little bit of chain rule with that sine 2x. But the overarching big rule that we have to make sure we start with is product rule. Okay, S prime G plus F G prime. I mean, we could take a GCF out, but usually, if it's a multiple choice, it could go a little further than this. They can factor 2x out, but you know, for response, you can leave it in any form to resolve it. Careful with that sine 2x. Derivative is cosine of u times u prime, so that times 2 needs to be involved with my g prime. Okay, next page. Okay, implicit differentiation. We apply this derivative method when the equation is not a function. Cannot be rewritten in this y equals form, like the previous problem, where your y and x are clearly nicely separated. If your equation looks a little bit strange with the y variable sticking out, multiple y's, or you see y raised to a power or square root of y, y stuck in a set of parentheses. So if that's the case, we know, okay, we're still going to go through our normal derivative rules. We should have to do a little bit extra when we come to y's derivative. We have to attach a dy dx as soon as we take care of its derivative. So immediately following taking the derivative, we multiply by dy dx, and then dy dx is now our derivative variable. And then after you find your derivative, you're just trying to algebraically move things around to solve for dy dx, and that's your derivative variable. So number one, x squared plus y squared equals 5 plus y. You see a bunch of y sticking out, so that's an indication that, oh, I gotta keep track of my dy dx. Let's go through this first one step by step. Make sure you're comfortable with the process. So every term looks like every term is nicely separated. There's no product, chain, quotient rule. It's just all going to be nice power rule problems. So x squared becomes what? 2x. So there's nothing new with x's. It's just the y's that has a little bit extra. Okay, x squared becomes 2x. Y squared becomes 2y, but we need to attach dy dx. Good. All right, 5 becomes 0. Okay, and then y becomes 1 dy dx. So I like to put that 1 there just because it helps us keep track of a coefficient that's in front. So you don't have to have that 1 in front. You could technically just say dy dx, but that 1 is a good placeholder. So when you move things around, you remember that if you factor dy dx out, there's still that 1 sitting there. So I think having that 1 there could prevent a future mistake. So you're done with the calculus here. Now you're just adding, subtracting, moving things around, try to isolate the dy dx variables together. They can factor dy dx and they can solve for dy dx. So problem, a problem is not going to say, hey, use implicit differentiation for this. You're going to have to kind of recognize the need for it. Right? So anytime you see y variables in strange places, that's usually an indication you got to do implicit. Any questions with 5? Okay, number 6, also find the derivative. We see the need for implicit because you see, multiple y variables, and y is not, it's not y equals
an expression in terms of x, you have the equation with y kind of sprawled over the course of the equation. So we know we have to definitely use implicits, but there's something else here, something a little sneaky. Product rule, right? I know we don't see parentheses, but the 2xy is enough for us to require product rule because we can merge them together. And 2x times y, there's a understood product between 2x and y. So in order to find the derivative, we have to go through product rule. And within product rule, we got to also take care of implicit. So yeah, it's a little, sometimes it's hard for students to see that because there's no set of parentheses. It doesn't announce itself, hey, use product rule here. You have to kind of recognize it there. I think the tendency is we see this and we say, oh, I'll just treat the derivative, 2x becomes 2, y becomes dy dx, and I'm done with it. But I have to take the time to actually, expand that out using product rule. And something else that could throw us off is what? Besides product rule, there's something else that could throw our answers off if we're not careful. What else do we have to be aware of with the problem? There's an operation here that could end up being a troublesome if we're not careful. What is it? What do we have to be careful about with this minus signs here?
Parentheses.
Yeah, parentheses, right? When you do product rule, you end up having f prime g plus fg prime. You want to protect that with a set of parentheses because that negative has to end up distributing through. So that's another thing that we have to be careful of with that minus sign in front. So what I did was after I applied product rule, I protected my two terms with a set of parentheses so I can remind myself, oh, I really need to take care of the negative with both terms, right? It's not just going to affect the first one, it's going to affect both of them. F prime g plus fg prime, 2 times y plus 2x times dy dx. And don't forget, another thing that I see students have trouble with is they think that they're just taking the derivative of the left side and not the right side. The right side is also being affected. The 1 doesn't stay 1, that 1 turns into a 0. So that's something small mistake that I've seen in the past as well. Solve for dy dx, you can choose to factor the 2 out and reduce, or you can leave it in that form, but make sure you don't cancel the 2's outright and do this, right? You want to go further, you gotta factor the 2 out from both the numerator and denominator, and then you can take the 2 from the top and bottom. Okay. Questions so far? You don't have to. This will be perfectly fine if it goes for a response, but usually on the AP exam, they tend to simplify, so you just have to know how to get from here to here. But this for response, they're not going to take any points off if you don't reduce. So step right before this, if you want to see it. So 3x. Okay, take a look at 7. What do we have to be careful about with number 7s? First, what big rule is required here? Chain rule, yeah. But this is a nested chain rule. There's a function within a function within a function, so we got to keep track of the 3 things here. But I made a suggestion as to how to make it a little bit easier to see the outer and inside and inner portion. So what can we do to make this feel a little visually more helpful?
3 out.
Yeah. Move the 3 out. When you move the 3 out, you're not applying any calculus process. You're just making it so that it's easier to really understand what that 3 is doing. That 3 is really raising the entire expression to the 3rd power. The reason that 3 is written in that form is because it's an easier way to write it without using a bunch of parentheses and brackets. So that's a shorthand way of writing this. This feels more cumbersome to write, but this is clearer for what we want to do, right? You can clearly see, oh, that bracket cube is outer, my inside function is tangent to u, and then I got to worry about, that u prime as well. So my suggestion is take the time to rewrite it, and then you can look at the problem from that bracket perspective, and you can see, okay, I got 3 things I gotta take care of here. So we take care of that outer portion first, that bracket cubed. Becomes 3 brackets squared, and then we take care of tangent's derivative. Tangent becomes secant squared u times u prime, so we gotta take care of its u prime. 3x squared becomes 6x, so we have to kind of link all these parts together. And also the important thing is that make sure that you're linking them next to each other and that you're not linking them within each other. Okay, so I know there's a function within a function within a function, but when you find the derivative, they're not going to be nested within each other. They're all going to be kind of pulled apart. So bracket q becomes 3 bracket squared, tangent u becomes secant squared u, and then u prime times 6x. So everything is all one term, so we kind of just rearrange it. You don't have to put that squared back in this form, but I wanted to show you this form because if it's on the multiple choice section, they tend to put things back in a nice clean form. So typically you're not going to see them writing the square like this. They're going to see them write the square like this. You want to work through number 8 from scratch with you? So number 8, it says if f prime of 1 equals 2, find p prime of 1, or p of x equals f of x cubed. So this, we're going to start here. We're going to work our way to p prime of 1. We see there's a function within a function, but the outer portion is function notation, but the inside portion is an expression. So we're going to still go through chain rule, okay? But we're going to keep them in the proper form. So p prime of x equals. Okay, so what can represent the outside derivative? Yeah, f prime, right? So there's no need to do any specific derivative rule. You just have to keep it in that function notation.
So f prime of x cubed, right? So this represents the outside portion, right? We keep the inside intact. Times. Now we're ready for the inside, so x cubed becomes 3x squared. So really, you're applying chain rule. That's the hard part. After this, you're just putting information in for x and trying to resolve as far as you can go based off of the information provided you. Okay, 1 cubed is 1, f prime of 1. What's f prime of 1? Do we have a substitution for this? 2, right? Now, if they did not provide a substitution for this, then you would have to leave your answer like this, right? But you can only go as far as what's provided for you. So in this case, I can make my way all the way down to 6. Okay, derivative of inverse at a point. We like to work, or I like to work my way around this chart. But let me kind of give you a big picture here first, the visual representation of this process. So this is the big idea. The idea is that if I have a function and inverse, they're always going to feel like you can fold over this dotted line, this y equals x, and the two curves will always overlap each other. That's when you know you have an inverse, a function and its inverse. And there's a special relationship with any of these ordered pairs. So if there's the ordered pair that lives on the function, there's going to be a ordered pair in the opposite order for the inverse function. So if there's an ordered pair 1, 4 that lives on the function, there must be an ordered pair that's 4, 1 that lives on the inverse. Okay, so that's the special property that a function and inverse have. But at their, I call them corresponding points because they are related in the sense that numerically they're just in the opposite order. The slopes at their specific points also has a numeric connection to each other. So if the slope at the original function is showing 7, then the slope of the inverse at its corresponding point must show the reciprocal. Okay. So 7 and 1, 7. So how does that help us? Well, normally the process begins where you're asking to find the derivative of inverse at a point. The first thing you do is you understand that, okay, any order pair that is living on the inverse, I can create the opposite order for the original function. And if I can find the derivative of the original function, then I can take that number and I can come around and flip it to get to what I'm looking for. Okay. So we're kind of moving our way around the chart. And basically, the problem is asking you for something on the inverse side of things, but you are given information on the function side of things. So you're using this information to get to that numeric value, and then you just flip it to get to your answer. Okay. So the first step is, let me read the problem here. It says, given our function is 2x cubed minus 3x, if h is the inverse function of f, so there it is, we have the relationship that f and h are inverses of each other, find h prime of -1. So I'm going to put that over here because that's really my goal. My goal is I'm looking for h prime of -1, but everything that's given to me is on the F side of things. So I'm gonna locate what information that I need, and I can come back and make my conclusion H prime of -1. So here's my chart to kind of help me move around. Okay, so that's the unknown. I don't know what H prime of -1 is, but I do know that -1 is the X value of my H function. So I'm just going to go ahead and put my order pair information on the first row. And so that's my step 2. Step 3 is that, well, if -1 is the X value of my inverse, then -1 must be the what? Y value of my original function, right? So I can say F of some X value equals -1. And this is where I can make that connection. Okay, so now I'm going to look at this puzzle that I've created and try to figure out, what X value on my function will produce -1. So I can replace -1 in for my Y value. So -1 equals 2x cubed minus 3x. This is not something that I can solve or algebraically factor. So I'm going to have to just go through a little bit of guess and check. So what if I just bring everything over to one side, keep the same equation, just make it a little bit easier for me to guess and check. So it's going to be an easy number to find. It'll be a small number close to 0. So I'm just going to start with 0. If I test 0, is this going to work? 0 minus 0 plus 1, is that equal to 0? It doesn't work. If I plug 1 here, 2 minus 3 is -1, -1 plus 1 equals 0. So there I have it. Okay, so there's my number. There's my ordered pair that I can build. So I know my ordered pair must be 1, -1 on the function side. On the inverse, it must be -1, 1. So now if this is the key that allows me to unlock the information from the slope side, because if I know my ordered pair is 1, -1, then I can find F prime of 1. If I can find the slope of F prime of 1, then that number is going to lead me directly to what I'm looking for. So how can I find F prime of 1? Yeah, let's get to the derivative, and then we can evaluate the derivative at 1. Okay, what's the derivative of F of X? 6x squared minus 3. Now I can find the slope of the F graph. So basically, we're doing everything on this side of things, right? We're trying to find that F prime of X, F prime of 1. Once I find that prime of 1, then I can take that number and I can flip it to what I'm really looking for. So F prime of 1 equals 6 minus 3 is 3. So F prime of 1 is 3. So therefore, yeah, F prime of 1 is 3. So therefore, H prime of -1 must be what? 1/3. Don't change the sign, just flip your numerator and denominator. Okay. Number 10 is in a sense easier because you just have to work your way around the chart. And sometimes problems may give you some information that you may not need to kind of see if you can sort through it, right? So just be careful that, sometimes they provide you some information that may not be relevant to see if you can just pull the information that's needed. So I like to start at the very bottom here. I know x2 is the x value of my inverse function. And if 2 is the x value of my inverse, 2 must be the what of my original? Must be the y value. So I've gotten this far without even looking at what's given to me, and I need something that will fill in and make this true. So, okay, I know f prime of 2 equals 4. That doesn't help me. F of 1 equals 2. That helps me because that fits into what I've established. So now, if I have 1 being the x value, I can find f prime of 1. F prime of 1 equals 3. So if f prime of 1 equals 3, then the derivative inverse at 2 must be 1/3. So just coincidence that it matches the same answer as before. It's not always 1/3. It's just because that's the case here. Now, what information do we not need in this problem? Yeah, so this is there to throw students off, right? So this is not even needed, but it's not part of this process, right? Your homework, pages 7 through 8. I'll check this on Wednesday. Today, what I want you to focus on preparing for this quiz tomorrow. Try to work through pages 21 and 23 if you can, and tomorrow morning I'll have help session 7:15. All right, come get your phones.
Go ahead.
Yeah.
Here's,
Thank you.